All right. So today we'll be talking and continuing on our sort of policy discussion and again, thinking about how modeling kind of plays a role into a lot of the decision making behind most of what we'll be talking about is regulatory requirements. Today we're going to be discussing two fuel standard policies. One, renewable fuel standards, also known as RFS, and the low carbon fuel standards, LCFS. So the RFS is a federal fuel standard, and the LCFS is primarily a California based regulation. We will talk about sort of the structure of these policies, how they're different, and how a lot of scientific and academic studies have contributed to some of the changes or even the instantiation of the policy in the first place. Oh, hang on. Actually, let me turn on the lights. Just noticed that was very dark. All right. So one of the common themes that we've been talking about throughout the class is thinking about transitioning to alternative fuel technologies. And so in this case, in the case of transportation, really what are the available fuels that can sort of feasibly be seen as an alternative to gasoline in the future. And so not all of these are necessarily created equal, but some of the most common alternatives that we think about. So compressed natural gas is one, electricity, obviously for electric vehicles. There are biofuels, which is a lot of what we'll be talking about today, at least with the first policy, and then hydrogen. Okay, so the Renewable Fuel Standard was actually first enacted as part of the Energy Policy Act of 2005 during Bush Jr.'s administration. And it was then extended by the Energy Independence and Security Act in 2007. And the main idea of this standard is fairly straightforward. So essentially, it wants renewable fuel to be blended into transportation fuels. And we increase every year up to 36 billion gallons of this renewable fuel by 2022. And just to give some context, the United States consumes roughly 150 billion gallons per year. And that could actually be plus or minus quite a lot, depending on how demand changes over time. And so, as you can probably imagine, in 2020, due to the pandemic, that consumption rate decreased quite a bit. So nevertheless, this regulatory requirement is administered by the US EPA. And there's a sort of combined set of goals in decreasing dependence on petroleum and also trying to reduce greenhouse gases from fuel use, which, as we'll sort of talk about, may be sort of less clear. So here is sort of the basic gist of how the original biofuel mandate looked like. So in the orange, you've got your conventional sort of gasoline, your conventional biofuels. and the quantity of this biofuels in billions of gallons sort of increases over time. You can see that the way that the biofuel is produced also sort of differs. So we think of sort of conventional as typical production methods through, for example, corn ethanol, but there are other ways to derive biofuels. There is a sort of broader category of sort of other advanced biofuels. One of the really big ones is thinking about cellulosic biofuels, and then biofuels specific as replacement for diesel. The way that we integrate biofuels into the system is by essentially mixing it with gasoline. And so when you go to the gas station and you pump up your vehicle, actually there is a proportion of that fuel that is ethanol, that is actually not just gasoline, and that actually is totally fine for your gasoline engine, sort of up to a certain point. And we'll talk about that sort of limit and what that means for this policy in a second. So the Renewable Fuel Standards operates with tradable credits. So every time you create a blended gallon of biofuel, this generates what's known as a Renewable Identification Number, or RIN. And basically, the way that we make sure that you are essentially using the correct proportion of biofuels is a requirement to essentially turn in a number of RINs for every gallon of gasoline that gets sold. So it really operates kind of, these RINs are essentially credits, right? And you can see in these charts some of the historical prices for RIN credits. And you can see how they've sort of fluctuated over time. And so this credit mechanism is essentially the market-based solution for incentivizing or essentially requiring the fuel producers to include biofuels into the fuel supply. There are sort of a couple different events that happened over time that have led to fluctuations in the price. And so, you have some exogenous sort of policy levers that can lead to changes, but it can also be demand and supply driven. And so you do see quite a bit of fluctuation and variation in prices over time. Okay. So in the middle of the 2010s, there is an issue that gets back to this idea of how much ethanol can we actually introduce into sort of the gasoline supply, and some of this is related to that issue I was talking about before. Well, once you introduce a high enough proportion of ethanol into your fuel mix, you can actually this can actually lead to issues in not even actually the combustion of the fuel in the vehicle, but actually the way that it's contained and sealed, because ethanol can actually degrade components such as the fuel connectors within the vehicle. So some of the lines running into the engine with the fuel injectors. And so there was a worry that vehicles should not exceed 10% of the blend of ethanol. And so there was a lot of sort of lobbying that was happening in the early 2010s that basically was saying, hey, you know, once we reach this this 10% limit, you know, we're going to have a really hard time essentially meeting the requirements for RFS. And so, you know, I just sort of suggest Googling, you know, RFS blend wall, and you can see sort of how much lobbying there was against the requirements from the renewable fuel standards. So blending beyond 10% requires more sales of E85 flex fuel vehicles, which, and I'll get back to that in just a second, but let me do a quick sort of lemma and talk about flex fuel vehicles. So you may have seen these little badge insignias on some vehicles. There are a couple different versions of this. There's also one with a green leaf that says PZEV, which is a partial zero emission vehicle. It's all kind of branding, but essentially what a flex fuel vehicle is almost an exact replica of a regular sort of gasoline engine, except they have built in several sort of really cheap technologies that help to allow the vehicle to use ethanol up to actually 85%. And the cost to an automaker to do this is actually only just a couple $100, you know, using different materials for the seals and for the lines. It's not a really sort of difficult thing to even retrofit existing gasoline vehicles to be able to take up to 85% ethanol. And actually, one of the interesting things about this is that oftentimes, you know, you might think about alternative fuel vehicles like electric vehicles as being maybe the most popular alternative technology to gasoline. But in reality, you know, if we consider this a true alternative fuel vehicle, these things are by far the highest selling alternative fuel technology on the road now. And the main problem is that so yeah, even a decade ago, you know, these vehicles account for something like 10%, over 10% of total annual new vehicle sales in the country. But of course, the big problem is that E85 is not really sort of readily available. I don't know how many people have even ever seen a station that offers E85. Most of them are going to be located kind of in the Midwest area, whereas, you know, the vast majority of the population are going to be located on the coast. And so there is no issue with driving these vehicles just as gasoline cars. And so, you know, the vast majority of these are driven as just a sort of conventional gas car and not actually employing the E85. And because of that, E85 is not a solution to the blend wall. It's less than 1% of annual gasoline demand, even if you have on the vehicle side the capability to actually use this. The EPA ended up sort of holding strong to their RFS requirements, and we ended up sort of bypassing the blend wall without any real difficulty. It turns out that using higher proportion of ethanol in the gasoline didn't really end up being a problem. And so shortly after the requirements, we saw higher proportion than E10 being used sort of throughout the country. And so we, quote unquote, broke through the blend wall, didn't end up really being too big of an issue. And so when a lot of these arguments were being made, it was during a period of time where the renewable fuel standards was undergoing a midterm review and sort of incorporating changes to the requirements. And so lowering the proportion or sort of total volumetric requirements of biofuels did not end up being one of the changes made to sort of the post 2015 RFS requirements. But there were some changes in how the biofuels were actually being required to be produced. And so on the left-hand side was the same sort of chart I showed before. And one of the ideas is that, when it was first introduced in 2006, 2007, there was this idea that, we give some ramp up time to some of the other production methods before sort of making it sort of a large proportion of the volume needed. And what you can see in the graph on the right, which does only just go to 2018, is that they ended up cutting down on the cellulosic production requirements because that technology did not sort of really pan out as being able to grow at the rates that were sort of initially expected. There are still lots of technical difficulties and challenges with cellulosic biofuels, unfortunately. And so that accounts for much of the difference that you see between these two charts. Yeah, and so, going back to thinking about the total volumetric requirements, 15 billion, that's right around your 10% level. And so it's still, a long ways off from, fulfilling the majority of the fuel use in the country, but still, I think at a fairly high volume, and clearly the sort of induced effect of having RFS is leading to changes in the way that the fuel supply is being provided in the US. Is higher volume possible? Well, I'll just give a kind of easy example. Here you can see in Brazil, there really was a rapid transition towards flex fuel vehicles, and Brazil does actually use a very large proportion of their fuel as ethanol. There are specific reasons why that fuel is sort of much more preferred in that country because of the availability of the fuel supply. But it does sort of point out that at least on a technological side, it is possible to get really sort of high level of penetration of biofuel use and flex fuel vehicle use. It can get pretty political. You can imagine that we're talking about, hundreds of billions of gallons of fuel, and so the market for that is really big and can have pretty sort of serious impacts on the sort of pockets of major corporations. And so just to sort of really keep in mind, right, by having requirements for biofuels, you're basically saying, use less fossil fuels, which means that you've got your, definitely a lot of the sort of big oil companies are a lot more against this type of policy. Whereas a lot of the sort of agricultural farmers whose crops end up being used for biofuels, they're going to get a lot of sort of guaranteed demand, and therefore sort of being able to drive prices up higher, and they're going to be making a lot more money from this. And so there's a really strong coalition of farmers in the Midwest who support this policy. And that'll play into important considerations in the future as we think about how this policy may change. And actually, before we get into some of the modeling aspects about RFS, I will sort of quickly note that in the new administration, there's actually a lot of sort of movement for future developments in RFS. In 2025, I believe, the renewable fuel standards are as sort of currently written, are going to lapse. And there's going to be sort of a big opportunity to think about what and how the policy should be structured in the future. And there are some sort of experts, and I'm sort of not as sort of vested in this particular policy as some, but there are some researchers at UC Davis who are already thinking about the reformulation of this type of policy into a more sort of LCFS-like policy, and we'll talk about what LCFS is later on today. But that would be sort of a sort of larger scale fundamental change where we think a lot more about connecting it with emissions rather than just having sort of these volumetric requirements. The one other possible change is actually the introduction of electricity into the renewable fuel standards, which is kind of an interesting concept. And actually one of the new developments is thinking about having these RINs that are for any electricity use in transportation and being used in the cellulosic market for credits. And so yeah, if any of that is kind of interest to you, definitely sort of keep your ears out for movement on this. It'll be sort of a really fundamental change to start including electricity as a fuel that's supported by RFS. It means that there's going to be even more sort of money sort of shifting from your traditional fossil fuels into supporting electric vehicle technologies. Okay. Okay, so a lot of these issues are definitely going to require quantitative analysis, right? So thinking about the emissions associated with their use, how might they affect the price of corn? What's the effect on the food fuel trade-off? And that's a really sort of big consideration for a lot of these types of policies where you're using these commodities that serve other end uses. And so by driving up the demand, you may be affecting sectors in ways that are maybe unintended or sort of not sort of really foreseen. And so one of the big ones for biofuels is that it'll compete with the food supply and therefore affect prices for one of these essential goods. And we'll see how that plays into some of this analysis in a bit. Okay, so let's talk about emissions associated with renewable fuel standards. Okay, so this I think is a really sort of nice overview of emissions associated with biofuels, the use of biofuels, thinking about the whole sort of life cycle emissions associated with not only the sort of combustion of that fuel in the vehicle, but also all of the upstream life cycle emissions that come from production of that of the crop and growing it, harvesting it, and then refining it and transporting. That whole sort of process is included here. And so we have three different types of fuels: corn ethanol, sugarcane ethanol, and soybean diesel. And there are a variety of studies and entities who have looked at the emission ranges of the emissions, the ranges of emission impacts compared to gasoline. And so for gasoline, if it's at zero, then you're saying that there is no difference with using this particular type of ethanol and burning gasoline. And really, your objective should be trying to get sort of a negative emissions difference, which means that the fuel that you're then using is cleaner than gasoline, and therefore you're getting greenhouse gas emission savings. So what you can see in this analysis is, let's just take a look really quickly at EPA. And so in the initial creation of the rule, they estimate that you get this minus 21, minus 61 or 57%. So you're only emitting 70 to 80% of what you would be doing with gasoline, and even lower, right? Something like 40% of what you'd be emitting with diesel if I use these sort of fuel sources. And so this is what drove a lot of the initial sort of rulemaking. And then there were a couple studies, really sort of prominent studies that came out a couple years later, sort of during the sort of midterm review of the renewable fuel standards, that showed, hey, wait a minute, there are some factors that we didn't really consider. And so one study by the National Research Council, found that corn ethanol could be anywhere between 25% better to almost 100% worse than gasoline. And there was a study coming out of Carnegie Mellon by Kim Mullins that showed a similar sort of range. And so, these retrospective analyses are really important to sort of understand and quantify these impacts, because it's going to be, you know, a really important consideration for whether or not we should even have this policy as a greenhouse gas emissions reduction device, you know, if it's cleaner than gasoline or if it's dirtier than gasoline. Yeah, and so making sure that you really get that right and you understand the uncertainties associated with it are really critical for this program. And really understanding the differences between why, you know, initial modeling had come up with these numbers versus why you get so much higher in some other cases. There has to be something really fundamentally different about the way that the work had been done. Okay, so in a life cycle analysis, you include this sort of boundary of what you want to include in the analysis, and so for those who are familiar with life cycle approaches, essentially, you know, you're going to go back in the sort of production stage up to a certain point before you decide to sort of make a cutoff. And that cutoff is somewhat arbitrary in nature. You always have to make some kind of internal decision about, you know, when I can sort of draw this boundary for my analysis. But I'm just showing here in this particular paper, so that this is the paper coming out of Carnegie Mellon, that shows, you know, where their boundaries are. So everything from in the production process, from the feedstock handling, all the way through producing the actual fuel for both corn feedstock and switchgrass feedstock. So importantly, this boundary includes, so determining the fuel yields, right? So this is the efficiency of like going from crop to gallons of your biofuels. And then there is this land use change, which ends up being one of the most important factors in determining these emissions. And we'll get back to this in just a second. So feedstock production, feedstock transportation, and then the fuel production, all of these are, I think, pretty intuitive to include. But the land use change has to do with, okay, if I were thinking about growing a particular crop in this area, right? You know, in the counterfactual, what would I have sort of grown otherwise, right? And that in itself will have a whole set of emissions associated with that counterfactual that you then have to sort of account for and measure in that difference for your analysis on how the land use change emissions are going to look like. Okay, and so from that paper, you can see actually we'll start on the right-hand side. These are distribution of greenhouse gas emissions for the production and use of different biofuel feedstocks. And this actually comes from a Monte Carlo based approach where they look at the uncertainty associated with all of those different steps in the life cycle, integrate that all into sort of this one distribution. And so you can see, okay, right below 100 grams of CO2 per megajoule, that's where your gasoline sort of baseline point is. And then you can see how the distributions are spread sort of about that. And you can see that corn ethanol and corn butanol, which the earlier analyses were kind of showing were better than gasoline. In this case, those distributions definitely look kind of to the right of your baseline. And so you actually have this the main difference between this analysis and so this is kind of the driving point for why the numbers in this study differ from the numbers in the EPA study, is because of this red bar, which was actually not included. And so this is indirect land use change, so ILUC. And this is definitely one of the more sort of controversial portions, both in the renewable fuel standards, in a lot of these analyses, but also probably more aptly for the LCFS. So we'll get into some more detail of how that affects directly with the LCFS. But first, I'll explain a little bit about this indirect land use change concept. So remember when I was saying with the direct land use, you're thinking about, in this counterfactual case, you know, what I would have grown in this area instead. The indirect land use change is, okay, I have reallocated this area to grow, you know, corn to produce biofuels, but there's still a demand for the food crop. And so what ends up happening is that you may end up getting some other farms to essentially produce that the food to meet the food requirements or demand that was displaced by now producing biofuels. And so a lot of this is actually being, there's a lot of sort of work in this area that's shown that as we start to grow more crops for biofuels, we end up importing a lot more food crops. And a lot of this is actually coming from Brazil, where they're starting to do deforestation in order to produce the food that was displaced from the biofuel demand. And this leads to a lot of sort of extra emissions. It's always controversial because this is, it's impossible to prove, right? Because you're talking about doing this counterfactual case that you have no sort of empirical basis to show. Like, you don't know that Brazil would or would not have done that sort of deforestation to grow more crops in the absence of this policy. And so, you know, at the time when this study came out, there was a sort of pushback to, you know, some of this indirect land use change that was sort of mirrored a lot of the pushback seen in the LCFS regulation. Yeah, and so, so yeah, before I move on, just recall that, you know, the sort of analysis and quantitative modeling, you know, is a really important feature of understanding the impacts of this policy and therefore how the policy may be sort of structured in the future. And you know, don't always assume that that the federal agency sort of got it right in the first place, because I think a lot of what this particular paper and several papers down the line have shown is that that the answer may actually be different. And actually, this particular work was done by a graduate student. So you know, you have the potential to make a big impact even as a student. Yeah, so in wells to wheels energy use and greenhouse gas emissions of ethanol, this is a slightly different study showing the boundary for their life cycle analysis. And so in this case, you can see explicitly the indirect land use change, displaced products. And so in this diagram, I think it's a little bit more clear to see the sources of direct emissions, and then sort of the side changes that are happening indirectly through your land use change direct and indirect land use change. Okay, so what about emissions from other feedstocks? And so this, I believe, is a study from Argonne National Labs, which looked at a whole bunch of other feedstocks. And so what if we produced biofuels from things like sugarcane, or from corn stover, or from sisgrass, or miscanthus, and it considers the contribution, it gives this really nice sort of breakdown of the emissions from any sort of particular source, right? And you can see the total amounts compared to gasoline. And in this case, they have land use change, but not indirect land use change. And you can see how that will lead to numbers that are lower than gasoline sort of across the board for all biofuels. So this isn't quite sort of comparing apples to apples with what was being shown in the previous study, but in this case, it's still sort of nicely demonstrating the relative differences in feedstocks, sort of broken down. And so in the chart on the right, you can see for all of the different pathways, the emissions level compared to gasoline, especially in comparison with and without land use change. And just to show, okay, how they compare between these two studies. So even though the ultimate answers are fairly different, if you sort of match up the components that are actually included within the model, you'll see that they actually agree fairly consistently. And so if you were to sort of subtract out the red portion of the indirect land use change, you actually end up getting fairly consistent numbers for the greenhouse gas emissions. All right. So the last thing that we'll talk about with renewable fuel standards are market effects. So how does it affect corn production? So you can see here, the share of US corn production for a particular category has substantially decreased in sort of the feed category. And so a lot of that is now being used to produce ethanol. And so this does kind of get to or provide a lot more sort of impetus for the analysis that is talking about how you're sort of displacing the use of this resource for fuel, and therefore, you know, the demand is going to look to other sources to make up for it. Some of that has been in increase in amount of corn that is planted and trying to get higher yields. That's going to compensate a little bit for, you know, this higher demand from fuel due to RFS. And it also has a really important effect on prices. So you can see how flat the corn prices were several years prior to to the introduction of RFS, and then how it sort of skyrocketed to almost 4 times its value since RFS was introduced. And so that is a really sort of significant impact on the economy for this corn product. And you can see why it ends up being a really sort of compelling proposition for farmers in the Midwest to provide this crop as fuel for transportation. Okay, so let's quickly take a 5-minute break here. And I'm happy to sort of chat about this program more if anyone is interested. All right, let's get back into it. So yeah, I think that wraps up our discussion about renewable fuel standards. And now we'll talk about low carbon fuel standards. So really, if we sort of zoom out and take a sort of 10,000 foot look at these regulatory requirements, you know, at the end of the day, the renewable fuel standards is really the sort of volumetric requirement for using some amount of biofuels, essentially, and possibly, right, in the future, it may include things like electricity, and you know, that is an important mechanism for helping to transition into the use of these alternative fuels. But what it doesn't do directly is think about sort of reducing emissions. And we can really sort of see that, right, from the analysis about, you know, there's a lot of back and forth about, you know, how much emissions are we actually causing from ethanol. But at the end of the day, it doesn't really care about that. It's really, as long as you're using it, right, you're fulfilling the requirements for RFS. So the low carbon fuel standard is kind of in principle similar to the renewable fuel standards in that it is inherently a mechanism to get us to use alternative fuels. But instead of a volumetric requirement, it's really based off of an emissions requirement. And so all the sort of signals in the low carbon fuel standard are making sure that you are transitioning to a fuel that's going to lower emissions over time. And so that's really sort of one of the fundamental differences between the LCFS and the RFS as it sort of currently exists. So in California, probably most, I mean, I'm sure all of you guys know who Arnold Schwarzenegger is. It's very interesting because, you know, when you think of Arnold Schwarzenegger, we think of, you know, his famous movies and whatnot, but actually, you know, one of his probably most significant roles that I think is really sort of understated or not really well known is the fact that he is responsible for this executive order S-107, which basically is the thing that caused AB 32 to happen. So the executive order preceded this bill, and it was basically saying, okay, we need to get to this carbon reduction level by 2050, and shortly afterwards, the state legislature passed AB 32, which for those of you who don't know is a requirement for the state to lower emissions by 2050 to 80% below 1990 levels. So I kind of think of AB 32 as kind of like almost like a Green New Deal type of thing for California, except we were, you know, a decade ahead of the curve, because it is a really, really optimistic, goal-oriented policy that says we have to, you know, reach this requirement, but it doesn't tell you anything about how it does that, right? And so over the sort of next decade after AB 32, we started to see a whole slew of policies getting implemented to make sure that we are sort of on track. And so, you know, it's kind of in my opinion, this is a type of thing that could be sort of replicated at the federal level with something like a Green New Deal, which may not necessarily tell you how to get there, but sets the sort of tone and precedent in policy to do that. And so out of AB 32, we saw the LCFS, which we're going to talk about today, but also things like cap and trade, the sort of new requirements for ZEV mandate. All of these policies came into place because AB 32 was there. And so, yeah, I think that is probably the policy that really puts California ahead of everyone for trying to reduce emissions. Okay. So after the state legislature passed a bill that basically required the low carbon fuel standards, the California Air Resources Board is the entity that is tasked with actually administrating that standard. There was an executive order that then required the California Air Resources Board to coordinate with the University of California, the California Energy Commission, and other state agencies to propose a schedule to meet the 2020 target. And so that University of California team was led by Dan Sperling, whom I'm sure most of you know or have spoken with. He's the head of the Institute of Transportation Studies here, and Alexander Farrell, who's a researcher at UC Berkeley. Okay, and so the really sort of novel thing about LCFS, and it's not the only policy that has sort of done this, but one of the sort of unique things about the formation of this regulation is that it is really sort of science driven, and even before the creation of the rule, relied on a whole set of sort of independent studies, right, in academia, and not just from members in the regulatory agencies, and not just sort of counting on stakeholder interaction. It is fundamentally sort of a science-driven derived policy. Okay, so general motivations. These are kind of coming straight out of that study, thinking about greenhouse gas emissions. In California, at least, you know, we've put a lot of emphasis into transportation policies, and that's kind of rightly so, because transportation accounts for the bulk of the emissions from our state. It's kind of interesting when we think about what is necessary to reach the 2050 goals, and why the state has taken such a strong stance at like decarbonization for transportation, even when there are, you know, perhaps other low-hanging fruit in other sectors, is that even if I were to entirely get rid of this 41% out of transportation, if this were entirely to be decarbonized, I would only be halfway to my 80% reduction goal, right? And so that is the reason why you see such aggressive policies, particularly in the transportation sector, where it is actually really difficult to sort of fully decarbonize. And you can see back when the study started, what was first sort of underway, that the projections of where our emissions would be going is sort of completely in the opposite direction of where we need to be. So, you know, these are the interim targets to get to this 2050 goal down here. And so something really drastic needs to happen in order to, you know, both not only sort of change this trend, but change the direction so that it's, you know, going downwards. And then this is in the baseline year 2004. So the study was being conducted, you know, in the lead up, eventually getting sort of finished up in 2007. But the baseline year that they were looking at is 2004, and so this is essentially what you have to work with, right? This is what we know the emissions are, and then the share of each of these fuels. Okay. So understanding gasoline baseline, I believe I've shown this figure before, right? This is a supply curve for how much potential fuel there is globally, and the cost of producing that. And so because this stuff is so cheap and there's all this uncertainty and variability, the whole idea behind LCFS is I'm going to drive all of this stuff up the supply curve until there are other potential fuels that can be used that would have lower emissions impacts than whatever you're seeing here. So forecasting future gasoline consumption. So these are models that I've mentioned before in our class. So this vision model in California, which is a stock turnover model with a whole bunch of sort of different parameter and attribute inputs that you can mess around with. So they were using this to try and figure out what the gasoline demand would be over sort of the next decade. And this is actually what it looked like. So gasoline retail sales by refiners in California, I guess we're, a little bit outdated, but you can see that there was, following LCFS, sort of downward trend in gasoline retail sales. So part of this obviously is coming from things like the recession and generally downturn in the economy that's leading to decreased consumption, but actually overall, we can attribute some of this to effects from LCFS as a sort of net sort of reduction in what we would have expected the gasoline sales would have been otherwise. Now, following sort of 2015, there is kind of like a small sort of uptick back up, but sort of given the rate of decline, it's sort of surpassed what was projected in that original 2007 study. To understand some of the impacts, you have to be able to sort of forecast cost estimates of your different fuels, and in that way be able to understand sort of how credit prices in LCFS would affect sort of the market. And so there's within the study these cost estimates that are based off of breaking down all of these costs that would go into the production of the fuel. And so you can see, again, a lot of uncertainty included in these results. And that is an important concept that has been coming up, in all of the studies that we've seen, is that, none of the results are just these sort of single point estimates. There are always doing sort of this sensitivity in order to encompass this range of outcomes that we're seeing here, even for the baseline of gasoline. Electricity costs are also included, and this is also a sort of fairly difficult type of thing, where you basically have to look at the supply of electricity and the corresponding wholesale prices, and where you estimate the cost will be for electric vehicles relative to gasoline. I think it's a little antiquated to kind of do this type of comparison. because the way that the efficiencies work out are not the same for gasoline. But this gives you a sort of rough idea of how expensive it would be to charge your vehicle for different sort of load profiles. So with a million, they estimate, so for 1 million vehicles charging, if you're in the summer or spring peak or summer and spring nighttime, you'd be paying something on the order of 50 cents to 40 cents for summer and spring peak, and then maybe below, dollars per megawatt hour, or below $20 per megawatt hour in the nighttime, and that translates roughly to anywhere between 75 cents up to maybe $1.75 per gallon equivalent. So definitely still quite a bit cheaper. Okay, and so that part of the study in estimating the costs was very important to understand sort of how the market would be and prices would be affected by the introduction of this policy. But then the other really important thing is to get at estimates of carbon emissions. And so this is the global warming impacts estimated by two different LCA models adjusted for energy at the wheel. And so right now I'm just showing one model called GREET, which is a model developed at Argonne National Lab. It's an LCA model that tells you that measures essentially the life cycle emissions of each of your different sort of fuel types. And so it gets pretty specific, right? We can look at emissions per megajoule for all of these different fuel types. And for certain fuel types like ethanol, we can actually go in and look at different production methods, right? So if it's based off of a coal-fired dry mill versus compared to cellulosic ethanol, right, you have vastly sort of different numbers. And remember, everything is being sort of compared to your marginal gallon of gasoline. Okay, and so the way LCF standard is actually, I'll have some slide on that later. I'll get back to that. So let's get back into the derivation of some of these numbers. So introducing life cycle assessment into policy. As far as I'm aware, I think this is actually one of the very first policies that include life cycle analysis. And so it's kind of really neat to see a lot of this fundamental research coming into play in practice for the development of this regulation. And so in the study, they talk about well to wheels. So over the emissions sort of over the entire sort of lifetime. So the GREET model that I was talking about, the one developed in Argonne, does include life cycle analysis, but there were a whole bunch of specific concerns that were brought up in this original study. So treatment of market-mediated effects. So how are things consequentially affected? And so even if I do this sort of life cycle emissions of this particular chain of events, that is actually replacing something else. And that alternative is one that you may need to consider because you can actually have substantial differences in what we expect the emissions would be with and without the policy. And that's one of the most sort of difficult things to measure. Land use change, and that's something that we talked about with RFS and will play a really important role here. Climate impacts of emissions. And so we think about greenhouse gas emissions, and we just usually folks just kind of equate that with, oh, CO2, right? But there are other types of pollutants. Methane, for example, is well known as something that can have much larger impacts per molecule than CO2. And so thinking about integrating all of that into one a uniform a uniform way of measuring emissions is important. And then thinking about inherent variability and limited quality in the data. And so again, this is kind of an emphasis on including uncertainty in your analysis. Okay, so returning to the topic of land use change. Again, this kind of chart, I think, helps to demonstrate this example. So if you have no sort of requirements, then maybe here's my forest and rangeland, and so I'll have land that I'm using for food production. So the direct land use change is, okay, if I start to use new land to produce the biofuels, that leads to sort of direct to these direct impacts in that land in region 1. If I then divert existing food production to produce those biofuels, well, that demand for food still has to come from somewhere. And so you then get this indirect land use change where in a different region, I may be sort of using this land to produce my fuel. And so that's what is, again, being measured under indirect land use change. So there was a model called LEM, which includes measurements of land use change, and that was being included in this regulatory policy. And so what you can see is that the numbers coming out of this model were really, really different from the numbers coming out of GREET. And in fact, this can play a really important role because 70 compared to 92, you're still cleaner than gasoline, and therefore there's some room in the market to do that. But if it's higher than gasoline, then really there is no incentive. In fact, you'd have to be paying more money in order to use this fuel that's probably a little bit less economical than gasoline. And so again, it just sort of points to the importance of getting this analysis right for policy, and the inherent sort of difficulty in dealing with these large sources of uncertainty. Okay, and so what does that mean for the actual standard and sort of how it works? Okay, so the way the standard works, right, is that, if I look at all of the fuel consumed in California, and then I figure out the emissions associated with that, I can then get this average emissions rate, which is going to be really close to, for example, the emissions rate for gasoline. And in fact, this compliance schedule shows, right, so prior to LCFS coming out, right, we assume that it's right about 88 grams of CO2 equivalent per megajoule. And then essentially the way the standard works is that, okay, now you just have this declining emissions requirement. And so, by 2020, I have to go 20% or so below that. Sorry, less than 20%. It goes from 88 down to a little bit below 80. So like a 10% decrease in emissions. And so you can do that a whole sort of bunch of different ways. In the technology forcing, you give a lot more sort of buffer time for people to start to comply with the requirements, and then sort of steep drops later. These are all sort of things that were thought about at the time. And then you have this accelerating curve, this linear one, and then this rationalized. And so one of the important things to keep in mind here with any sort of goal-oriented emissions-based target, such as like AB 32, where you say 80% below 1990 levels by 2050, all of those, you could in theory go right up to that last year and then drop down, right? But the impact on climate change is based off of cumulative emissions. And so the ones that decreased the most at the beginning will, right, get compounded benefits of those decreases over time. And so the cumulative emissions by 2020 will be different for all 4 of these compliance schedules. So the study ultimately makes these 22 concrete recommendations. So they want the scope to cover providers of non-liquid fuels, so electricity, natural gas, propane, and hydrogen. We know that a lot of these fuels are really sort of viable alternatives to gasoline, and that we shouldn't just use liquid-based fuels. Otherwise, you're sort of picking and choosing winners already, right? You want to give all of the different fuels a chance to participate in this program. Baseline should cover most recent year and be applied uniformly. Upstream emissions should be included through LCA, including land use change. And this one was pretty clever, and actually has been replicated in other sorts of policies. So the way that it works right now is that, if I produce a fuel in a certain way, then CARB, through through their own studies or analysis, comes up with these default values for how much it assumes, like production of electricity or ethanol production has, so in those grams of CO2 equivalent per megajoule. And those values are really, really pessimistic. And so you always get sort of the worst end of the deal by using these default values. But if you are a producer or provider of these alternative fuels, you can actually go to CARB and say, okay, hey, like, look at the pathway that I'm using to produce this fuel. It actually has this emissions rate, which is lower than your default value. And so if you do that, then you can actually be able to claim a different emissions rate than the ones that are sort of default by CARB's analysis. And this is a nice incentive for producers to really actually try and reduce the emissions associated with production, because you can actually claim that emissions decrease as a benefit in the credits. Credits can be traded in banks. Compliance happens through fees, and then they also recommended that there is a certification and auditing process, which is how it happens now. There's this whole like clearinghouse and auditing procedure for LCFS credits. Thinking about environmental justice and sustainability issues. And that was sort of really ahead of its time. This popped up again in 2017 when LCFS was getting reauthorized. Oh no, I'm sorry. That's No, I take that back. I'm thinking of cap and trade, but environmental justice and sustainability issues are an important component of any sort of climate policy. And given how hot this topic is these days, LCFS really was sort of forward thinking in starting to talk about these issues even back in 2007. Program review and cost analysis. The University of California also recommended to do more research on the topic. Surprise, surprise. There's some maybe internal bias there. And so in 2009, following the release of the study, CARB incorporated a bunch of recommendations from those studies. It goes through this whole stakeholder engagement process where they conduct public workshops for stakeholders to engage in the rulemaking. They submitted a bunch of studies for external peer review, and then they have a public hearing time with tons of comments that were submitted. Challenging LCFS. So the rulemaking was finalized in April of 2009 and slated to begin on January 1st of 2011. And then in December of 2009, the Renewable Fuels Association and Growth Energy, which are essentially these big US ethanol lobbying groups, filed a lawsuit to challenge the constitutionality of LCFS. So this is kind of where the politics are meeting the science, right? So why are they challenging it, right? Because a lot of the indirect land use change that ended up being incorporated into the policy where we did end up including things like indirect land use change made ethanol look really bad, or especially corn ethanol. And so there was an injunction filed against the implementation of LCFS. In April of 2012, there was a stay of the injunction, and everything ended up getting ruled in favor of California. There have been several more appeals to challenging LCFS, all of which were lost. And so LCFS continues to go on. Okay, so as I'm mentioned before, the framework, it's an intensity target rather than a cap. So grams of CO2 per megajoule. You can kind of think of this as kind of like the efficiency standards, right? It's a target based off of the emissions rate associated with the production of all of these different fuels. But it does include all of the life cycle rather than just tailpipe emissions. By having a performance standard, you are sending a consistent signal to industry, you're tightening the targets over time, and it sets the targets in such a way that the signal is not ambiguous. Like everyone knows what they have to do in order to comply. And because it includes sort of all of the fuels, you have flexibility for fuel production by not picking specific winners or losers in a technology, which is not necessary to say that as a good or bad thing. It's just different, and we do hear a lot of criticisms for certain types of policies like the ZEV mandate, which inherently does place value or has to place value in an arbitrary way on specific technologies. The regulation itself is imposed on fuel providers, so all the refiners, blenders, and importers of transportation fuels. The carbon intensity of the fuels is based off of global warming intensity. So these potentials are the way that you can standardize across different greenhouse gases. So you can have CO2, N2O, methane, and all of these, and we figure out what the equivalent is per megajoule of energy. Okay, and then this last bit I think is always a little bit confusing for some folks, but we adjust the carbon intensity based off of the drivetrain differences. Okay, so what does that mean? So when you do the grams of CO2 per megajoule in the use, you are going all the way up to the fuel going into the vehicle, right? And so if we use gasoline as a baseline, both electricity and hydrogen are scaled by this energy efficiency ratio to account for differences in the drivetrain, because it would not be comparing apples to apples if you just looked at the fuel at the point at which it goes into the vehicle. So if you think about it, the combustion of gasoline happens in the vehicle, but the combustion of like natural gas for electricity happens upstream. And so if you don't account for the differences in drivetrain, you're going to get really skewed differences in the emissions when you are not going all the way to adjusting for the energy efficiency of that drivetrain. Okay, so this is the energy efficiency ratio adjusted carbon intensities. So this one right at the top, carb OB, is your default gasoline value. That's the baseline. And then similar for diesel right here. And then the reason why you actually see all of these different points along this really sort of broad range is exactly for the reason that I was saying before about how producers can actually demonstrate their emission pathways to the California Air Resources Board. And so this is a survey of all of these different producer pathways that have been submitted for consideration, or not even submitted for consideration, but are actually being used to award credits. So there are some producers of hydrogen that can produce it with a carbon intensity of 0. Which means that you are producing the hydrogen entirely from, renewable resources, right? And so that is what this sort of range is showing, is that people can produce, renewable diesel with a carbon intensity between, say 10 and 60 grams of CO2 per megajoule. And depending on the pathway, you're able to get a different amount of credits from LCFS. So the 10% reduction target by 2020 ultimately ended up looking something like this, where you have a 10% reduction by this level. You'll recall that there was that injunction filed, and so the compliance requirements actually flattened out for a little bit. But in the meantime, a lot of producers were sort of going on anyways, sort of assuming that it was going to happen. And so there was a significant amount of banked credits that were building up during this time. And then sort of as the policy got more and more aggressive, that's when those banks were sort of drawn down to allow for meeting meeting the LCFS standard. So several years ago, LCFS ended up getting extended. And so post 2020, we will still see a continuation and decrease in the carbon intensity of fuels as required by LCFS. Okay, I'm actually going to skip a couple slides. So the way that the way that LCFS actually works is that you have a whole bunch of regulated parties, and so this includes petroleum importers, refiners, wholesalers, and approved alternative fuel producers. So anytime transportation fuels are either imported, refined, or sold, all of these regulated parties have to enter information into what's known as the LRT, the LCFS reporting tool. And that tool basically keeps track of all your credit awards and your deficit positions for every individual regulated party. And so if you sell gasoline and it's at a higher carbon intensity rate, you start to build up a deficit. And the only way you can get rid of that deficit is if you provide LCFS credits. And so that means you either need to produce an alternative fuel to generate those credits to pay off that deficit, or you can purchase those credits from someone else who's producing that alternative fuel. And so the money, the way that you can think about this is that alternative fuel producers are really essentially getting subsidized by payments from traditional fossil fuel entities. And so a portion of the money being spent on gasoline and on diesel are going into supporting all of these alternative fuels. Right. Okay. And so that's essentially what I'm saying here. There's actually other ways that you can do it as well, which I didn't mention. So you can blend low carbon biofuels, and so it's a similar principle as RFS. And then the other one is to improve efficiency of your refinery operations. And because LCFS, it goes across the whole life cycle production, if you can reduce the carbon intensity by improving efficiency in your refinery, then you get the benefit of being able to count those emissions reductions. So credits traded, and so this shows the offset, right? And so the deficit is seen below here in the white and in the black. And so this is gasoline and diesel. And so you have to, on the flip side, be producing credits, which are from a whole slew of different sources. You can see at the beginning, a lot of it is from ethanol sources. That's all the stuff in red. And then you see in the blue, which is growing over time, those are either biodiesel or renewable diesel. And that's accounting for credit generation. And then the last one that I'll sort of quickly mention is electricity, right? We know that electric vehicles are starting to increase a lot more. And so you can see in the yellow here, that increase happens over time and really sort of starts to pick up in sort of the last couple of years. So LCFS credit prices, in early 2017, there were lots of banked credits, but credit deficits started rising higher than the credits coming in, which means that you have to start relying on some of these bank credits. And this actually led to a pretty substantial rise in credit prices. It's been a while since I've checked LCFS credits, but I believe that they're still actually around $200 per credit these days. Okay, modeling the LCFS credit market. So this is a sort of economic analysis, thinking about the credit system design and cost savings. And so this is thinking about extension of a program like this to a national level. And so there was an optimization model designed of a national LCFS to kind of replicate California's policy design. And so this kind of gets at some of the interesting studies that came out sort of after the implementation of the existing LCFS. They assumed pretty similar carbon intensities, probably a little bit different in some cases, particularly with the electricity grid, for example, which is fairly different from California's through the rest of the country. But for the most part, the carbon intensities they assumed in this model were fairly similar. Yeah, and so some of these use similar models that we've talked about, again, with the vision, and being able to understand the effects of trading and banking credits. And so, with a lot of the sort of structural models that we discuss in the class, you're able to construct these analyses that can sort of replicate or simulate what's happening at different scales and resolution. So in this particular case, going from a California-wide model to a sort of national level model. Okay, let me see. Do we have enough time to talk about this? Actually, so I'm actually going to end a little bit early today. So the last thing that I want to talk about is electricity and LCFS. But I think what we'll do instead is to cover this in Wednesday's lecture. I don't think we have quite enough time to get through all of the electricity part of LCFS. And I do want to leave a little bit of time for questions in case anyone has any. And then a couple administrative things to talk about before we wrap up. So hopefully everyone's gotten feedback for their projects. Those are actually coming up pretty quickly. In 2 weeks, we'll have final project presentations. And so I will sort of make a random order of people to present on Monday and Wednesday. So just note that those will be due then. And then the final report for the actual project is going to be due after all the presentations are done. And so you'll be able to get some feedback from the project presentations as well. Yeah, so if anyone has any questions about feedback on the project, feel free to reach out to me. And then lastly, so the fourth homework has been posted. I know that at this period in time, that you'll need to start spending a lot more time on the project. And so homework 4 is definitely a bit sort of easier and shorter. it's basically kind of messing around with an online tool. So there isn't like any math or anything that you guys will need to do. So that hopefully shouldn't take you guys too much time. Yeah, and so that homework will be due in the same sort of time frame, so due next Wednesday. But definitely it'll be a lot easier than previous homeworks. Okay, and so why don't we end here, and I'll stick around for a couple of minutes if folks want to chat a little bit more about LCFS or our RFS.